Hello everyone, I'm Mons Anderson, architect at Mail.ru Cloud Solutions and also Tarantool Technical Chief Product Manager. Today I will tell you how we build our S3 compatible storage, how it works, which solutions were successful and which ones were worth changing if we were start from scratch. Earlier, I already had a talk 3 years ago about this system. We designed data and relations model from AWS documentations and behavior. We divided systems into logical blocks based on components we had. I'd been planning for scaling from the first prototype to production and about live system upgrade principles. Also, it was told about hardware we'd been using for our system. These days, architecture looks like this. So today, I will guide you through its creation step by step. Development of our own S3 started on top of Mail.ru Cloud internal storage. Mail.ru Cloud, it's like Dropbox. For the first, I'm going to tell you how it works and what it does. Storage consists of servers with a lot of disks. On average, a modern storage server consists of 36 disks, 12 to 14 terabytes each. Earlier, disks were smaller, but today it's almost half a petabyte of raw storage space within one server. Then, disks from different storage servers are combined into so-called pairs. A pair is a minimal storage unit. In fact, it's a bunch of disks mounted to a specific partition at a specific path. Pair keeps files identified by their hashes. So a pair, it's a historical name that has been preserved to these days. Earlier, it consisted of only 2 disks, but today it may be on 3 disks, and there also can be various hybrid storage options, such as 3 by 2, like in RAID 5. All pairs are stored in PairDB. PairDB stores all pairs, their states, free space, failure probabilities, and recent errors. It can also communicate to pairs itself, update their state, check their health. In other words, PairDB is a general snapshot of the state of all disks in our system. PairDB is an application based on Tarantool. 2 words about Tarantool. It's an open source in-memory computing platform that combines a flexible data schema, either relational or key value or even document, and fast and easy onboard application language that give us a way to build performant applications with ease. Tarantool is hosted on GitHub and published under simplified BSD license. Tarantool relies on the following principles. All data is stored in memory, but changes are persistent. It uses write-ahead logging for persistence. Access to data is similar to relational databases. Various index types and kinds. There could be multiple indexes, composite. They could be tree, hash, R3, or bitmap. Tarantool has built-in support for synchronous or asynchronous replication, which gives you choices for reliability or responsiveness. It also has flexible virtual sharding for scaling. Application platform uses event-driven architecture with coroutines, just like in Golang, and has a lot of libraries for network communication and data manipulation. In other words, we use Tarantool either as a fast in-memory relational or key-value database, or as an application layer, and have no need for any other databases. All the databases in our projects relies on Tarantool. So go back to architecture. Files are stored on pairs, and to know which pair contains which file, we need another database, FileDB. Source mapping, compliance between a file and the pair it lies. Like the file is stored on a pair Z, and it has size X and some attributes. The next important service in this system is the Nylon, a gateway to databases. It's a single entry point, allowing us to work through a single interface with both PairDB and FileDB. This is a stateless service, so it may be scaled, that performs query balancing, knows the sharding of FileDB since FileDB keeps all the hashes, and also keeps track on pair health and availability status. Also, we need to put content into the storage somehow. We have a service for this purpose, the streamer. It provides two HTTP methods, put method to upload content to the storage and get method to retrieve it from there. We choose HTTP because it is very popular and convenient protocol for transmission large amount of data. When a client accesses the streamer uses Nylon to query PairDB, finds out which pair is best for uploading, then transmits data via WebDAV to these pair storages. Upon successful completion, a hash of file is persisted into the FileDB. In fact, any storage server is Nginx with disks mounted at specified paths. We can use streamer to upload a blob to storage, delete it, rename, or check its integrity. In other words, WebDAV is a convenient interface for low-level interaction with blobs on the storage. So, we looked through the internal basic storage at the time we were going to launch S3. Using the put method, we could put arbitrary content there and receive a hash as an identifier of this blob. Using this ID, we was able to come back later and retrieve this blob. But that was not enough to implement S3. In the S3 protocol, in addition to storing objects, there is more functionality, requirement to identify an object by its name. Also, we need to store metadata, additional properties of objects, access to objects via HTTP, and fine-grained access control. Also, we wanted to have an architecture for further growth with near linear scalability, and of course, we wanted it done yesterday. I mean, as soon as possible. First of all, we had implemented a simple daemon for Amazon S3 API protocol support. It is XML-based and uses the same HTTP endpoint for transferring either object contents or metadata. We did not need to invent something new here. Protocol is nicely described and well documented by AWS. As an entry point, we put Nginx before the daemon. It is used for SSL termination, load balancing, and some kind of business logic written in Lua, metrics, logging, and request tracing. Next, we took Tarantool for storing the S3 metadata. S3 daemon queries the database for metadata, but the content itself was stored in an internal blob storage via the streamer. Let's talk how S3 works. The user can create a bucket, a collection of objects. A bucket is addressed by the host name and is a subdomain of the service. Within the bucket, a user can create objects. The object ID will be part of the URI. The content of the object is a blob, an array of binary data that will be stored in the storage. The object also has some attributes: name taken from URI, access control lists, and other additional or arbitrary attributes. All they are stored in the metadata storage. The normalized schema of this may look like this. There are projects that own buckets. Buckets contain objects, and object may be composite. Objects may be uploaded in parts. There are two additional tables for object parts: uploads and chunks. Projects also have access credentials and billing. Since we're making a B2B service with paid access, we need resource accounting and billing in this scheme. Billing was also implemented as an application on Tarantool, and our main database just queried it upon requests. At this step, we had created a working system that can be used. Objects and metadata were stored, main API support was implemented, money was counted. But there were a few things missing before we able to go into real production. First, the system of rate limits. If you run the service without it, then at peak load, we could unpredictably overload some parts of our system. We had to put the rate limiter at the earliest stage of request processing. Thanks to the S3 protocol, we know the bucket just from the URI. So we could limit requests per bucket. The rate limit system by itself must be sufficiently fast to withstand the load that comes to service. Here we use Tarantool again. This is the cluster that we create of 21 instances configured as a big replica set with local storages. Configuration changes like limits and defaults are propagated via replication. Each bucket is served strictly by a single node. When a request is received for a specific bucket, the node responsible for it is calculated via consistent hashing. Within this node, current rate is calculated using the token bucket algorithm. The performance of a single node is over 100,000 requests per second, so rate limiter is capable to control over 2 million requests per second. The rate limit system, based on the current load indicators and limits set for a bucket, replies whether the request can be proceed or not. Limit checks are performed at the earliest stage of request execution, protecting all other elements of the system from excessive load. Also, under load, it's quite difficult to create responsive system without the cache. S3 implies multiple access to the same objects. In other words, it's a hot storage. In the usual case, access to a single file is served by full chain of services. We access streamer, FileDB, PairDB, storages. However, multiple access to files are optimized with local cache. The cache is multi-layered and implemented using Nginx, local SSD, HDD, and RAM disks. Frequently asked question. We did not use Tarantool for cache because with Nginx and file system, we can make cache tiering from RAM through SSD to HDD, and this is very convenient to serve blobs. We have large objects with maximum size of 32 gigabytes, while Tarantool best suits for caching only small objects. This was the first version that led us to production environment. It had some pre-calculated capacity. Take a note, there is no scaling options. But it was good enough for understanding product needs, market requirements, and that it will grow. That first step was rather successful. Our service became more and more popular, and the planned capacity began to gradually fill up. So scalability became priority number one. Also, we had encountered some maintenance issues and found a need for automatic failover. Our S3 Daemon made requests for metadata using the Tarantool protocol. In place of the original database, we installed another Tarantool application, which acted as a proxy router for the metadata requests. From the point of view of the daemon, nothing has changed. It continues to access the database using the same protocol. But the router was able to provide an active failover. In other words, we were able to check the availability of the nodes, silently pause during switches and failures, and so on. And we did not modify the application layer itself. The next issue that had to be taken care of was sharding. The system grew, the number of objects exceeded 1 billion, and it was necessary to provide capacity for further growth. Let's go back to the data schema. There are projects, buckets, credentials, and billing. These are entities that are very likely not to grow beyond the limits of a single instance in the foreseeable future, either in terms of size or in terms of requests. This means that there is no point in sharding them. So we have moved them into a separate instance, which will remain unsharded. This allows us to manage projects and buckets more consistently, since there is a single unsharded database. There is also objects that grow linearly. At start, there were thousands of them, but now their number is measured in several billions. Objects, along with their parts, had to be taken into sharded cluster. We have divided the scheme, but objects need to work with buckets. The object always belongs to a specific bucket. Plus, the ACL access control list works on the bucket. Therefore, for each shard with objects, we keep a shadow copy of each bucket. In addition, during object modification, during query execution, we need to count the volume for billing. So each shard has counters from billing. We also added a few more tables during this transformation. We add recycle to destroy old projects that are deleted or frozen and to clean up them, and queue for background tasks, meaning the main storage can perform background tasks that need to be done on the whole cluster. And support for lifecycle was added to the shards that allowed us to implement object lifecycles. So we go back to the sharding. Since we took some of the data to the shards, we need a sharding proxy. It would be possible to reuse the router for this role, but a separate sharding proxy, which is responsible only strictly for sharding logic, allows us to keep routers much simpler. Let's take a look why we did not take a ready-made solution for sharding, but instead created our own custom sharding function. Let's see how it works. We have 256 available shards. We allocate a range for each bucket using a consistent hash function. It's simple. Just as we use the consistent hash function to determine whether an entity belongs to a shard, we define the starting shard and take the range from it. Range has constant length. In other words, if we take the bucket, we can say that all its data will always be stored on a specific subset of all shards. This allows us to reduce the impact of some buckets on others and simplify the work of MapReduce queries when, for example, we need to list bucket objects. To do this, we need to pull all the shards where these objects are stored. The objects, if objects were on all shards, then any list operation would affect the entire system. But with our function, it affects only a specific subset. Each object belongs to a specific bucket. So when we access an object, we access an object by name in a bucket. In other words, we can define a function for an object, not from the entire available range of shards, but only from a subset of its bucket. We take the object, pass only a subset of its buckets into the function, and get a specific shard. This scheme allows us to achieve the following goals. There is no request that could access all shards at once, and most frequent requests access only one shard directly. So sharding is implemented. There is a sharding proxy. All that remains is to go from the router and from main database with metadata to the sharding proxy. For example, to create shadow copies. When we create a bucket, the main storage must create a representative of this bucket on all shards where it should be present. So sharding is done, but everyone knows the biggest problem with sharding is, of course, resharding. It was important to us to do it without downtime, since the system was already in production and has clients. I'll show you the principle of leaf migration on another interesting production case, when we've been forced to merge separate projects. This is diagram of our cluster after the implementation of sharding. We had Nginx S3 API, router, primary database with projects, sharding proxy, and shards. I did not mention internal blob storage since it doesn't matter for this case. But previously, I skipped the point that at a certain stage of the project's evolution, there was a product task. Let's launch another S3 storage, an icebox. It's like Hotbox, but only for cold data. In fact, it is the same storage, but just working at different URIs and without caches. Icebox was in fact less popular than Hotbox, so it lived without any sharding for quite a long time. As a result, we decided to abandon it and combine Hotbox and Icebox into one service called Cloud Storage, simply separating storage classes by hot and cold. And the goal was, from outside, everything should remain as it is. From inside, it should become one service. And of course, no maintenance window, no downtime. Luckily, the buckets in the systems didn't overlap, and they could easily be moved and merged. But the clients used both endpoints, so we had to solve the problem with the lack of downtime. We could not just turn off all service and copy its data. So we divided the migration into several stages. First, we synchronized the primary storages that were responsible for buckets. Upon bucket creation, we do the following. The database receives a request to create a bucket, for example, in Hotbox. It queries another database, in this case Icebox, for an absence of such bucket. If there is a bucket, the database says that it can't be created, and it's synchronized as an existing one. We use Tarantool here, and performing such cross-database queries is done easily using Tarantool to Tarantool connector. In the storage that was supposed to take all the data, I mean sharded Hotbox, we had a property for projects and buckets that tells where this entity is stored. It could be stored locally in Hotbox. It could be in Icebox, then there is no data from it in Hotbox. Or it could be in the migration state. If the bucket had the migration flag, then the request was executed first to the new storage, to Hotbox. And if it was not there, the requests were redirected to an alternative storage. Next, we switched HTTP traffic. Since the API could handle both Icebox and Hotbox requests, we were able just to switch traffic without downtime by simply migrating hosts and adding the corresponding entries to Nginx of Hotbox service. After the traffic was redirected and all went to Hotbox, Nginx and the API Daemon of Icebox could be removed. Next, we launched a background migration process that worked inside the Icebox database. It traversed all projects and their buckets step by step, sets the migrating flag for them, transfers data, and sets the local flag when the migration is complete. After the data migration, we no longer need the old storage, and we remove the remaining parts of the old system as well as support for the migration status from the code. The same principle were used for resharding from old storage to sharded. Here are them. Mark all buckets as non-sharded. All requests to them went to original non-sharded storage. New buckets were created immediately within the sharded storage. Then took buckets one at a time, set the migrating status, then transfer objects of these buckets. To allow this process to be long in time, we must perform requests according to the following principle. Read in the new and only then in the old system. Create objects only in the new. And if we need some update, then we should perform it within two phases. If the new one doesn't exist, copy it from old system to the new one and then update it. A final touch to our system would be dynamic SSL support. In S3 storage, you can set your own domain for accessing a specific bucket just by using CNAME. But if you need HTTPS, you should provide SSL certificate for your own domain. As I said, Nginx is responsible for SSL termination in our system. In this case, this is not regular Nginx, but OpenResty, Nginx with Lua support. That allowed us to teach our Nginx to serve arbitrary certificates quite simply. Moreover, we needed to give certificates dynamically without having to register them in configuration file of Nginx. We used Lua extension, which allowed us to read certificate from any source directly during the TLS handshake phase. So we took Tarantool as a certificate store. This allowed us to manage certificates from the outside and provided extremely fast returns. A separate daemon was also implemented, whose task was to regularly update certificates that were issued using Let's Encrypt. As the last note, I'd like to tell what would I keep and what would I have done differently if I had developed the same project again. The first point must be out of failover. I'd install all the tools that are required for the out of failover since the first failures after launch were due to its absence. After experience of this project, all subsequent projects and products were launched with this in mind. The second one is sharding. Quite a lot of problems were caused by resharding. It is easy to start with it, much harder to implement it in a live system. If you need scalable system and at a small scale, better use sharding from start. And always take a note on features that could break things. I've missed S3 versioning. Initially, it seemed that this is not a very popular feature. It became extremely difficult to integrate versioning into the architecture of a live system. And which decisions were good? Data model. History of our product has shown that as the service evolved, we matched the Amazon data model pretty closely, so we could implement required features. Another point is sharding scheme. I would support the same range sharding across buckets since this allowed us to distribute requests from different buckets well across large cluster. It's very reliable and fault tolerant. And of course, I will keep use of Tarantool. Tarantool was the key driver of our rapid development. It greatly helped us with the evolution of the service, its modification. We easily worked with data, transformed and sharded storage on demand, and kept a good separation of application logic of API and data logic inside the database. Thank you for your attention. If you have questions, I'd like to answer them.
Thank you, Mons. So guys, please use the question form to ask your questions. And while people are typing, I hope, Mons, what would you suggest, what would you recommend to people who are just thinking about creating such product? If they have the stage where they're just planning the architecture, which would be the hottest point for them? What would you recommend to pay attention to?
The hottest point is, I think, scaling. When we build a system that must serve infinite amount of objects, we think how to scale every single point of our system. We must have an answer on how we scale if something went bigger. How to scale database, how to scale traffic, how to scale requests, and of course monitoring and automatics. We should know that we are reaching some capacity problems. We should monitor our system and know the system limits. Without monitoring, we will be blind and the problems arise suddenly.
Thank you. So we have no questions at the moment, but we still have time. So maybe you have some advice for our listeners.
The advice maybe if you do something that already invented, like it was for me, I just creating a service that was a partial copy of AWS S3 service. Just read the documentation clearly, understand how it could be created in different ways, then try to use it. Use modules and APIs to touch the systems with your hands and understand how it works and why it works. It was very helpful experience because our ideas of how S3 should work was different from how S3 should work in real production. So just investigate the system before starting to write the code.
So that would be a good investment, really. Thank you, Mons.